this lesson on differentiation from the first principle. So, differentiating from the first principle. Differentiation is about slope of functions at a particular point. So, we try to find slopes of functions at a point as the function moves in the Cartesian plane. And functions, if it is not a straight line, the slopes are not uniform. So, you find a slope at any given point using a straight line at that point, so that at the point of tangency, the slope of the straight line will be equal to that of the curve too at that particular point. So we say differentiating from the first principle because in our coordinate geometry at the lower level, we consider how to find the slope of a straight line that is changing y over changing x. And that is changing y over changing x, which is y2 minus y1 divided by x2 minus x1. This is the first approach that we have been using to find the slope of the straight line. So the same approach is going to be applied to find slope of a function at a particular point, hence the name first principle. So the theorem is from this principle, and when you know this principle, you apply it on the function to find the slope. So let's try to analyze what is happening in the plane. Assuming I have a function like this, and the function moves this way, and there is a straight line joining the function f of x. If I name this point P and the next point here Q, PQ is a chord. Some will describe it as a secant because the line can cross the curve. If it crosses, then the entire line will become a secant. But if it is just touching PQ like that, then the line is a chord. If it is a chord, then what we are saying is that at this point we have x values here and then f of x. Then we also have another value xn. So when you put Sn into this function, it will produce f of xn. So what we are saying here is that if I try to push this secant down, the line will behave like this. So that P will remain standstill, but Q will move down, and this will be Q1. In that case, if you look for the corresponding value on the x-axis, you will see that x is reducing from the original xn backwards. So let's call this one xn minus 1. Again, if I begin to push, maintaining the position of P down, x is also moving from xn to minus 1 to xn minus 2. So gradually, as Q moves from this point towards 2, you will see that X values are also reducing towards 0. So gradually, by the time Q will be tangent, PQ will be tangent, then that line will be here. If it is a tangent and Q sits here, then by that time, X values are gradually approaching 0. So we say that if you know the limit of the chord, you know the slope, if you know the slope of this chord PQ, then as you pick the limit, the small changes approaching 0, the slope of the chord will now change to become the slope of the tangent. So we normally determine the slope of chord PQ. If that one is done, then we pick the limit of that slope, then we get the slope of the tangent at point P. And that is differentiating from the first principle. So we are going to deduce a rule from this analysis. Good. So we have the Cartesian plane, and there is a function moving in the plane this way. If there is a chord, PQ, then we try to find the value here, x. Then the functional value will be f of x. Then, if from here there is a small change in x, then the value for x here will be x plus h, because x has moved an additional interval of h. So the value at this point will be x plus h. And when x plus h is evaluated into the function, then we produce f of x plus h. So from our elementary knowledge in slopes or gradient of functions, if you want to find gradient PQ, then it is going to be changing y over changing x. And some books will say this is the y1. Others will say y2. So if it is y1 here, y2 there, it is changing y over changing what? X. And this one become an x1, x2. So the slope of chord PQ, is now going to be changing y over changing x. And it is y2 minus y1 over x2 minus x1. Which implies that per this analysis, my y2 is f of x plus h. That is the value at this point. And the y1 will also be f of x. Good. Then divided by changing x, which is x2, this is the x2, and this is x1. So we have x2, which is x plus h, minus x1, which is also x. So from this, we can say that changing y over changing x, which is the slope of the chord, is now f of x plus h minus f of x. When you check the denominator, they will cancel. And the value here is what? H. So this is the slope of chord PQ. But per the initial analysis I made, if you want to move from x2 towards 0, then the Q will also be moving towards the P. So it will come to a point that x values are approaching 0 and PQ will now become a tangent. So as the small changes approaches 0, we use limit. So limits of the slope of the chord will give you the slope of the tangent at that particular point. So we want to find the slope. When you take the limit as small changes approaches 0, then the slope of the chord becomes the slope of the tangent. So we take limit of both sides. So lim as s approaches a particular point, h. Sorry, the changes are now as h approaches 0. Because the change is now called h. As h approaches 0 of changing y over changing x, that is the slope of the chord. When you pick the limit, it will be limit as, h approaches 0 of the other side, which is f of x plus h minus f of x all over h. And in Leibniz notation, as the limit as changing y over changing s, he denoted it by dy dx. So the limit as h, the small changes approaches, the changing y over changing x is now called dy dx in Leibniz notation. So the dy dx you see, or you have been seeing, is the changing y over changing x. And it becomes limit as h approaches 0, f of x plus h minus f of x all divided by h. Changing y over changing s is now dy dx. So you pick the limits as h approaches all the small changes. Some books will use delta s, telling you the small changes approaches 0 of the functional of this difference divided by h. Then you get the slope of the chord. So this tangent. So this one gives you the slope. It gives the slope of the tangent line at a particular point. So anytime you are asked to show from the first principle, you can go through the processes and arrive at the answer, or you can quote this for identity or formula and use it. If you can quote, you quote, and then you put in the values, then you simplify, you get the answer. Good. So let's take an example. First example, we want to find the derivative of a function. We have to find the derivative of y equal to s squared from the first principle. So if you are asked to find from the first principle the gradient or the derivative is the same as the gradient or the slope or the dy dx. So note the terms. When they say the derivative, the derived function, the derivative of that function is the slope. It is the gradient. It is the dy dx. So we know that we have f of x, which is the function. Please, this is the solution. F of x is given as x squared. And per the identity we just show, we will need f of x plus the change. So you put in x plus h into the function and it will give us x plus h all squared. So the derivative, which is dy dx, will now be equal to the rule is x limit as h approaches 0 of f of x plus h minus f of x divided by h. And in that case, we put in our f of x and f of x plus h, so that it will be limit as h approaches 0. The numerator will now be x plus h all squared minus f of x. Please, our f of x is now x squared. So you write x squared divided by h. And from our ideas in limit, as h approaches 0, the numerator will be 0. That will, if you put in 0 here, it will be x squared minus x squared, and it will be 0. And the denominator too will be 0, so indeterminate. Then we have to apply our knowledge in limits by simplifying the numerator. So let's expand. Use our algebra. So we have dy dx now equal to, in algebra, let's expand. This is perfect square. Limit h approaches 0. So if you expand this perfect square, you have x squared plus 2xh plus h squared minus s squared divided by h. And we can now simplify. S squared will cancel s squared. And you have limit as h approaches 0. When they cancel, we have 2xh plus h squared divided by h. And we can now factorize h out because h is in every term. So if you factor h out, it will cancel that of the denominator too. So that we have dy dx now equal to limit as h approaches 0 h of 2x plus h divided by h, and it is now limit as h approaches 0 2x plus h, and as h approaches 0, 2x is independent of h. Therefore, that one becomes constant. And 8 goes 0. The answer is 2x. So from the first principle, the derivative of y equal to x squared is now 2x. Let's take another example and appreciate what we are talking about. From the first principle, we have to find the derivative of this function. 1 divided by x from the first principle. And we need to know our solution. We need to know our f of x. So from the function, from the question is y equal to 1 over x. So this is our f of x. And if you put in x plus h, which will be f of x plus h, and the value will now be 1 divided by x plus h. So from the first principle, we quote dy dx equal to limit as h approaches 0. F of x plus h minus f of x divided by h. And from the question, we know our f of x plus h, which is 1 divided by x plus h minus f of x, which is also 1 divided by x, all divided by h. So as h approaches 0, what you are seeing there will be undefined. What you are seeing there will be undefined. And then we need to simplify. Check the numerator. The numerator alone is a fraction, which you have to find LCM, which is also being divided by another function h. So to simplify this, we write limit as h approaches 0. Better still, let me put it this way. We have 1 on x plus h minus 1 over x, all divided by h. That is the whole scenario. So if you pick LCM for this side, we are going to find LCM of this, and it is x into bracket x plus h. So when you pick the LCM, this side will be x minus, if x also divides the next factor, then the result there will be negative of x plus h. So that this function now turns to limit as h approaches 0. The whole of this is now this. So it is now x into bracket x plus h. Then the numerator is now x squared x minus h divided by h. So that is what is happening. Good. So we took LCM of the term here. And when you find the LCM is x into bracket x plus h for that particular function. So having known the LCM, this fraction will now turn to this. When you pick LCM, you get this fraction. And then the whole thing is also divided by h. So this x will cancel x here, they are negative positive 0. Then the whole thing will be divided by h. So we write limit as h approaches 0. The numerator is now negative h divided by x into bracket x plus h. Then when you turn that one to multiplication, it will 1 on h. This one. And by our algebra, still as h approaches 0, it is undefined. Because 0, the whole thing will be undefined, so they will cancel. H will cancel h, and it will be limit. As h approaches 0, the numerator is now negative 1, and the denominator is x into bracket x plus h. Good. And as h approaches 0, the denominator, you have to put in the h, which is 0. And the whole function is now negative 1 divided by x multiplied by another x. And the answer is now 1 neg 1 divided by x squared. So this is the answer for the function when it is differentiated from the first principle. We are going to try a third example. We are going to try a third example of y equal to axn by the general rule. Good. If you have a function of this form and you are asked to differentiate, that is find dy dx or the slope of such a function, it is always y equal to ax, and then dy dx is given by a n x n minus 1. What it means is that if you have a function, just use the degree or the power to multiply the coefficient of that function. So you multiply n and a where they are all constants. So when you multiply a and n, you get a n, then you take away 1 from the power, and that is the general rule for differentiation. So if you are differentiating, and the concept is not about differentiating from the first principle, you don't go through a long process to get a differentiation or the differential coefficient, but just multiply the power and the coefficient, then you take away 1 from the power, and that is differentiation. So what it means is that if the function is a quadratic function, because you are going to reduce the power by 1, when you differentiate, the result becomes a linear function. And if it is a cubic function, when you differentiate cubic function, the function goes to quadratic function because you take away 1 from the power. Example. If y equal to 3x power 4, find dy dx, or find the derivative of such a function. So to get dy dx, per the general rule, you are going to multiply the coefficient and the power, and it will be 3 multiplied by 4x, and the result is 4 minus 1, and we get 12x exponent 3, and that is the dy dx. Finish. You don't waste your time to go through the long process of differentiating from the first principle. This is the general way. So anytime you have to differentiate and it's not specific, just use this rule and then you get the answer for any polynomial function. We have to find the slope example 3. So we want to find the slopes of the following functions. So the first one, number 1. Solution number 1. When you find dy dx, don't forget that if a function is a linear function, the power is 1. So by default, we don't write them. And we are going to write dy dx of the first example, and it's now 2x power. The power will multiply. 1 times 2 is 2x power 1 minus 1. And the result is now 2x power 0. And place 2x power 0, power 0 is 1. And we don't write 21 because they are multiplying. So if you don't take care, you write 21 as the answer. That 2 is a coefficient, which is a multiplier. It is multiplying 1. So the answer is 2. Again, if you are to differentiate a constant function, that is the slope of a constant. Constant function is uniform. So the slope is 0. But how do you know? Per the general rule, this constant function is polynomial of degree 0. So we have 3x power 0. And we normally write 3. So once it's degree 0, if you apply the general rule we have just considered, our dy dx will now be equal to 0 times 3. And the answer will be 0 here. X power 0 minus 1. And it goes 0 times the whole thing will be what? 0. So anytime you find the slope of the constant, you have to get 0. You have to get 0. Let's try the next one. I think this one is a set. So to get the slope of the third one, this is the second solution. We're going to consider the third one. Solution 3. Let me use the function you see there is x power half. Y equal to x power half. So apply the principle. Dy dx is now going to be 1/2 x exponent half minus 1. The rule says subtract 1 from the power. And then the power must also multiply the coefficient here. And we simplify, we have half x exponent negative half. And per the ideas we have in indices, negative exponent changes to 1 over. So the whole function that if we want to simplify, we have half times 1 over x exponent, now positive half. So the negative index has now changed to positive index. And when we multiply numerators and denominators together, it is 1. And what is done is now 2 roots x. And that is the answer. In general, if you are to differentiate polynomial function of the form y equal to 3x power 3 plus 2x power, let's change the function to say 5x power 2 plus 7x plus 1. There are several functions: cubic function, quadratic function, linear, and then constant function being put together. The rule says that you are to differentiate term by term, as we did individually. So dy dx of this function is now differentiating the first term alone, and it will be 9x squared. Then you differentiate the second term, and the result will be 10x. Differentiate the next term, and the result will be 7. Differentiate the constant term to what? 0, and you are done. Given that y equal to 4x power 5 plus 3x power 4 minus 6x. Find dy dx at x equal to 1. What this one means is that you have to find the slope of the function when x is 1. That is the differential coefficient at x equal to 1. So you need to find the derivative of the function, then you put in 1, then you get the answer. So dy dx is now equal to 1 in solution. When you differentiate the function, you have 20 x exponent 4 plus 12 x exponent 3 minus 6. And we are now to find dy dx at x equal to 1. What it means is that we are going to put in 1. And the function is now changing to 20 1 exponent 4 plus 12 1 exponent 3 minus 6. And when you put in 1, we have 20 plus 12. 20 plus 12 minus 6. And the answer will be 26. Thank you.